Now, what we will do is provide the arguments and the formalism that actually takes care of the medium dependent effects on propagation of electromagnetic waves. Generally, there are two routes to describe propagation of electromagnetic waves. One route is what we had just developed in terms of the gauge potentials after defining their gauge fixing relation. And the second route is deal with variables, those are by themselves gauge invariant. The first set of variables appears when one talks of gauging the electromagnetic action, and the second one or second approach is what we are familiar with when we deal with Maxwell's equations. If we recall, then in this context, we probably have come across two variables. One of them is mu and another one is epsilon, and these two are usually called the optical constants. There of course exists another one, optical constant, but that we will talk of later. At the moment, to make connection with things we know already, we should keep in mind that what variables we are using in either of these two formalism should be related to each other in some perceivable form without compromising on their mathematical structure. So, these constants, those go by the name of optical constants epsilon and mu. Should be related to the form factors that were introduced while defining the polarization tensor pi mu nu. So, we first try to gloss through the ideas that lead to these form factors. Those go by the name of transverse form factor and the longitudinal form factor. What is shown in the slide, on the top of the slide, is something that goes by the name of Feynman diagram. It essentially also describes the photon self energy tensor. That is also defined in terms of a symbol capital pi of mu nu. The index or the Lorentz indices correspond to the wavy lines, those are the photon lines. One of them is considered here as mu and the other one is nu. And this self energy correction, that when computed using formalism of finite temperature field theory, then it actually splits up into pieces, those signifying vacuum part and those signifying the medium dependent effect, at least in a situation when higher order corrections are not taken into account. So, leaving this detail aside for this discourse, let us move on to the new developments with this. So, here what I have written in the equation 1 is the way the polarization tensor can be written in terms of the form factors and the tensorial structures. The quantity q mu nu actually refers to the longitudinal structure of the second rank tensor, and r mu nu q mu nu with a negative sign in between them defines the transverse structure of the polarization tensor. This is what one usually finds when one is dealing with isotropic and homogeneous medium, and if the medium is not isotropic and homogeneous, there is a external field that is there in the medium and that is maintained from outside, then this polarization tensor would also admit an extra piece. That extra piece we will discuss when the time comes with appropriate emphasis. Pi t and pi l, they are in general functions of momentum, the force velocity of the medium, the temperature and the chemical potential. So, if we consider their structures, those were dictated by the requirement of field theory, quantum field theory, then the Hermiticity condition would tell us that these form factors and their complex conjugate should be identical. So, they better be functions of 4 momentum square or higher powers. The second issue is the Bohr symmetry that demands under momentum inversion and exchange of mu and nu, nothing should happen to the polarization tensor. So, these form factors, then since the tensorial structures automatically are quadratic and they take care of it. So, the tensorial structure satisfying these constraints implies the form factors should be functions of 4 momentum dotted with the medium velocity square onwards, not single power. Why it is not they can't be dependent on the single power is the reason that under charge conjugation this whole thing has to be invariant, and if it has to be invariant, then it better have the powers of u even, and that can happen only when it appears in the description as k dot u square or something like that. So, it is omega square, that is what should come. The hermiticity condition also tells that this particular polarization tensor below the pair production threshold should not admit any complex part to it, what usually accounts for pair production. If the 4 momentum is large enough to produce a pair, then that is what it should be. And the same argument tells us that mu should be, power of mu should be even. So, it can be a polynomial in powers of mu, where each term in the polynomial is of even power, or you can construct a variable something like sine hyperbolic function and cos hyperbolic function or tangent hyperbolic function, but out of them we need to pick up one that is even. So, the cosine hyperbolic function is the one that survives to be incorporated here. So, while one is evaluating this particular Feynman diagram, at the end of this evaluation, the final expression should not contradict what we just have discussed. The structures of these tensors q mu nu, r mu nu, and there are no ands at the moment, are defined in the following slide. What we have defined as a modified metric G tilde mu nu is something that has been appended with introduction of another piece which is dimensionless, but has a momentum structure. And the q mu nu, which is the longitudinal tensor, takes care of the longitudinal part of the, or projects out the longitudinal part of the polarization tensor, is given in terms of the 4 velocities u tildes and a normalization factor that is obtained when these u tildes are contracted. So, we would like to note the following properties of the transverse and longitudinal form factors, and those are the following. In the static limit, when omega is equal to 0 and k tends to, there is a momentum tends to 0, pi transverse vanishes and pi longitudinal provides omega p. I think it is the square of that. And the piece that we did not discuss, that was identified with the third optical constant, or the appearance of the third optical constant, something that shows up or puts up its appearance in presence of an external field, is pi mu nu with a prefix p. Now, if we look at this general tensor decomposition and form factor, then first thing is the Bose symmetries demand that under mu going to nu and nu going to mu and k going to minus k, simultaneous joint operation, the corresponding part should remain invariant, actually follows from the following argument. Epsilon in any case picks up a negative sign when the indices are exchanged. So, there is a negative sign from there. The k that appears, lone k that appears in this expression, it picks up a sign under k going to minus k, but these two when considered together, then it is even. So, Bose symmetry is satisfied, and the hermiticity here, that is to say complex conjugation and of the polarization tensor plus taking transpose, that also is satisfied. Under charge conjugation, the factor U tilde picks up a sign, then it tells us that the terms those are present with chemical potential should be odd to compensate for this effect, and parity and time reversal invariance. Actually, the parity and the time reversal invariance would be compensated by the Levi-Civita symbol and the factor of I that is sitting over there, where at the end of the day we come to realize the magnetic field that should be present should have a spatial role with a spatial form in the expression for the scalar form factor pi p of k. Then temperature, chemical potential and magnetic field. So, this particular slide actually elaborates on what I have just mentioned, and same is true for here. The explicit form of the polarization part pi p has something that is density and temperature dependent, that comes as a combination of number density of the charged particles divided by their mass. The issue of the medium characteristics, whether it is relativistic, ultra-relativistic or classical, actually enters through those factors. So, to bring the whole discussion to a form, we see that the equations of motion finally can be reduced to 3 equations, and these 3 equations are independent of each other if there are no external field present. So, you can see that there is an equation for the A parallel, that form factor associated with the gauge field's degree of freedom in the parallel direction, and quote unquote the way we have defined the perpendicular direction and the longitudinal direction. And each one of these form factors, they depend on the constituents of the media, and depending on the composition, the solutions are going to be dependent, and if the solutions are dependent on them, then the variables that describe the spectropolarimetric features should also be dependent. Just for a little note, this pi p of k, the form factor in the non-relativistic limit and weak magnetic field, takes a form which is given at the end of the equation 4, which is given by the ratio of 2 powers of the plasma frequency divided by the energy square minus Larmor frequency square, and that is multiplied by the Larmor frequency into the energy of excitation. What one can do to study the medium characteristics are look at the values of the transverse form factors and the longitudinal form factors for a specific situation like temperature, when it is comparable to the mass of the constituents, for a situation where the temperature is greater than the mass of the constituents, or for the situation where it is less than the mass of the constituents, which is a classical situation, and same for the chemical potential. Okay. So, with this beginning, we would like to take a pause before we start up again. Thank you.